When I was in elementary school in English class, we used to listen to this old teacher read books really slowly. Me and my friend would get bored pretty quickly, so we started exchanging notes. Not long after, we got caught passing those notes, and the notes were read to the class, and so the cliche goes, we were embarrassed. But we decided that we wouldn't have our notes read aloud to the class again, so we started passing encrypted notes using the Caesar cipher to change the letters in the words so that only we could read them, using our birthdays as the shift number. Eventually, we got caught again, and we thought we were so smart because the teacher looked very confused when she saw nothing but gibberish written down on those notes. And instead of being heralded as child geniuses, as we were only 9 years old and using encryption, we were mentally evaluated.
The Caesar cipher is pretty easy to break. If you have some encrypted text, all you have to do is rotate through all the different possible combinations until eventually you spot something that makes sense. So we've seen that the Caesar cipher is pretty weak, and that's mainly because every letter in the message is rotated the same number of times. So why don't we just rotate each letter a different number of times and keep that information in a number? But then comes the problem of how do you communicate that number secretly if you don't have a way of encrypting stuff yet? The Caesar cipher is what we would call a symmetric encryption method, because when you do something to the input, you simply do that in reverse to the output and you get your input again. But modern day encryption uses something called asymmetric encryption, so that when you do something to the input, you actually have to do something very different to the output to get it back to the input. Modern asymmetric encryption algorithms today are really complicated, and we use really big numbers so that it's very computationally difficult to reverse them and brute force it. So, a lot like the original problem with the Caesar cipher, it's still possible, though really expensive, to just throw a lot of computer time at an encrypted message and eventually you find out the answer. The problem with relying on this brute force security is that it's not future proof. We're going to create faster computers, we're going to create new algorithms, and eventually, given enough time, those messages are no longer going to be secret. The strength of RSA in the early 2000s was only 512 bits, which back then, yeah, would take thousands of years of compute time to break. But today, with modern computers, it would take a few days to maybe a week. So those messages are no longer secure. And you can bet that there's information from the early 2000s that's still valuable today. So let's talk a little bit about quantum computing. We already know of a quantum algorithm called Shor's algorithm, which on quantum computers, which are almost within reach by the way, would be able to factor these 2048-bit keys in just a few hours. So if making encryption standards bigger and stronger only works for now, how do we create a system that will work forever? The answer lies in our fundamental approach to the problem. Instead of creating an impenetrably strong encryption algorithm, we figure out how to make a tamper-evident encryption message. And this is only possible because of some quantum physics properties. So, because of a couple of properties of quantum physics, and with the use of some really, really expensive science hardware, it's possible to, on the receiving end, know if somebody else read the message before you. So, by sending little bits of information at a time, when you realize that somebody else is listening in, you can just immediately stop sending and leak practically no useful information. Combining this with regular encryption means that that little bit of information you leaked is just totally insufficient for them to figure out what was being said. So again, one of the drawbacks of quantum communication protocols is that it's really expensive. Another drawback is that it's really slow. Sending this precise information, precisely calibrated photons is really, really difficult work. So the bandwidth is not very high. You wouldn't be able to play a video. You probably wouldn't even be able to text on that level of bandwidth. But what you can do, you can secretly distribute those keys we were talking about. There's finally a solution to send small amounts of information with total secrecy, ensuring complete security of any encryption protocols. Currently, a lot of research is being done to try and figure out a way to expand the range of quantum communication. One of the issues with sending really precisely entangled photons is that they're not stable. Over distances of more than like 10 kilometers, they become totally garbled, and it's impossible to definitively know whether somebody read it or if it was just some channel interference. Again, the really big problems and the reason why this isn't going to be accessible to just the average dude is it's extremely expensive and extremely difficult to get a hold of this hardware, and both sides need this hardware. You can't just install a quantum chip or whatever and then talk to your buddies on their regular ass iPhone. It just doesn't work that way. Everybody involved needs a new physical thing. So until that becomes the standard, it's just going to be regular encryption for now.